fun thing you can do with transverse waves is you can polarize them, and so that's last up today, polarization. So we're imagining I've got a string and I want to send a transverse wave along the string in this direction. So I could move my hand up and down, or left and right, or of course any other direction perpendicular to the direction the wave is going to travel. Light waves from the sun don't all oscillate in the same direction, and so light from the sun is called unpolarized light. But if you reflect on light from the sun, unpolarized light from the sun, off a shiny surface like water, then the light that reflects off is partially polarized. It's only oscillating in some directions. And if you shine unpolarized light at a polarizing filter, only the light that is oscillating in the same direction as the holes in the filter will get through. And so then the light that comes out the other side of this, it's all oscillating in the same direction. And so that is now called polarized light. Now, polarizing filters are just slots. They are just slots all in the same direction. But of course, for light waves, the slots need to be very, very thin. So if you're looking at a polarizing filter for visible light, you are not going to be able to see the slots. They're far too small. And of course, we have all looked at polarizing filters for light because that's what sunglasses have on them. So polarizing sunglasses, they just look dark. You can't see the slots because they're so narrow. Okay, and then this is where things get weird. So I'm going to imagine shining a light at a polarizing filter. My filter is vertical, but the light I'm shining at it is going to be polarized on a diagonal like this. Now you might think, well, this is on a diagonal and that's vertical, so they're not the same, so nothing is going to get through. However, light is an electromagnetic wave. That means that it is an electric field oscillating in one direction and a magnetic field oscillating perpendicular to that. Both of these fields are vector fields. And so what we're looking at is a vector thing. So this diagonal polarization has a vertical and a horizontal component. And so the vertical component can get through. So the light does get through, but not all of it. And you can actually, you don't need to do this anymore, but if you have done Malice's law, then that tells you how much is going to get through. Okay, so the light that comes out the other side is polarized, it's vertically polarized, but it's not, I should have done it a bit bigger, it should be exactly the same size as that vertical component there. So it's not, this light's not as bright as the light that was shining on there because some of it hasn't got through the filter. Okay, if I now put another filter in the way, and this filter is going to be on a diagonal, and the idea, I know my diagram's not very good, but the idea is that that one is exactly 90 degrees compared to that one. So now it hits this one, and once again we can split this one into a component parallel to the filter and a component perpendicular, and it's just this component that gets through. So you can see it's getting smaller and smaller, so it's the light's dimmer here than it is there, and dimmer here than it is there. So just that component gets through, but some of it does get through. Okay, now the reason that is so weird is that this light here is diagonally polarized, and as I was saying before, the idea is that this filter is exactly 90 degrees to that one. So if I tried to pass this light through that filter directly, nothing would come out because that is perpendicular to the polarization here. So there's no component of this perpendicular to it. But if I put an extra filter in the way, I can end up getting something out at the other end. Okay, the last thing to say before you have got a question is just that you can make polarized waves. And here is a very simple diagram of a transmitting aerial. This is what they look like in questions. Basically, the way you make an electromagnetic wave, the way you make a radio wave or some other kind of light, is you have an alternating current here, or an alternating voltage, and that is going to create, it's going to push electrons up and down this aerial. And so that's how you make a wave that is, all of the waves are oscillating in the same direction. Okay, and so here we have a very standard polarization question to finish today. Okay, so we've got a vertical aerial transmitting vertically polarized radio waves, and they initially hit a vertical aerial on the other side. So to start with, the intensity that is detected is maximum, and the signal to the detector will be maximum because the aerial is in the same direction as the transmitting aerial. And then as you turn it, you are going to get smaller and smaller components of the radio wave, so the signal is going to get less and less and less, and then by the time the aerial reaches horizontal, then it's perpendicular to the direction of polarization, so you're going to get no signal at all. And then remember, we've got to go all the way to 180 degrees, so then as we keep going, we're going to get a small component, and then the component's going to get bigger and bigger, so we can get more and more, so the signal's going to get bigger and bigger again until we get to 180 degrees, when we are once again in the same direction as the polarization, so our signal is back to maximum. That's a very standard polarization question there.